In this video, we're going to talk about a core data structure used in compilers, the abstract syntax tree. To briefly review, a parser traces the derivation of a sequence of tokens, but this by itself is not all that useful to a compiler because the rest of the compiler needs some representation of the program. It needs an actual data structure that tells it what the operations are in the program and how they're put together. Well, we know one such data structure. It's called a parse tree, but it turns out that a parse tree really isn't what we want to work on. Instead, we want to work on something called an abstract syntax tree. And the abstract syntax tree is really just the parse tree, but with some details ignored. We have abstracted away from some of the details of the parse tree. And here's an abbreviation that you'll see. ASTs stand for abstract syntax tree. So let's look at a grammar. Here's the grammar for plus expressions over the integers, and we also have parenthesized expressions. And here's a string. And after lexical analysis, what do we have? Well, we've got a sequence of tokens, again, with their associated lexemes telling us what the actual strings were. And that gets passed into the parser, and then we build a parse tree. And here's a parse tree for that expression. Now, I should stress that this representation, the parse tree, is actually perfectly adequate for compilation. We could do our compiler using the parse tree. This is a faithful representation of the program. The problem is that it would be quite inconvenient to do that. And to see this, let me point out some features of the parse tree. First of all, you can see that the parse tree is quite verbose. So, for example, we have here a node E, and it has only one child. So when there's only one successor of the node, what is that really doing for us? Well, we don't really need the E at all. We could just put the 5 right here and make the tree smaller. And similarly for the other single successor nodes. Furthermore, these parentheses here, well, these are very important in parsing because they show the association of the arguments with respect to these two plus operations. It shows that this plus is nested, this plus down here is nested inside of this plus up here. But once we've done the parsing, the tree structure shows us the same thing. We don't need to know that these were inside of parentheses. The fact that these two expressions are the argument to this plus already tells us all we need to know. And so all of these nodes in here are also in a sense redundant. We don't really need that information anymore. And so what we prefer to do is to use something called an abstract syntax tree that just compresses out all the junk in the parse tree. So here is a abstract syntax tree or a hypothetical abstract syntax tree that would represent the same thing as the parse tree on the previous slide. And you can see here we've really just cut it down to the essential items. We have the 2 plus nodes, we have the 3 arguments, and the association is just shown by which plus node is nested inside the other. We don't have any of the extraneous non-terminals. We don't have the parentheses. Everything is much simpler, and you can imagine that it'll be easier to write algorithms that walk over a structure like this rather than the rather elaborate structure we had on the previous slide. And of course, again, it's called an abstract syntax tree because it abstracts away from the concrete syntax. We suppress details of the concrete syntax and just keep enough information to be able to faithfully represent the program and compile it.